Lesson 7. Hypothesis testing with a normal distribution. You can test hypotheses about the mean of a normally distributed random variable by looking at the mean of a sample taken from the whole population. For a random sample of size n taken from a random variable x that follows a normal distribution with a mean mu and a standard deviation sigma, the sample mean x bar is normally distributed, with x bar following the normal distribution with the same mean mu, but this time a variance of sigma squared over the sample size. The distribution of the sample mean can determine whether the mean from one specific sample, small x bar, is statistically significant. Let's do some examples. A company sells juice in cartons. The amount has a normal distribution with a standard deviation of 3 milliliters. The company claims that the mean juice in a carton, mu, is 60 milliliters. An inspector thinks that this is overstated and tests a sample of 16 cartons, finding a mean of 59.1 ml. Stating your hypothesis clearly, test whether there is evidence to support this complaint at the 5% level of significance. We're testing to see whether the mean is being overstated, so our null hypothesis H0 is going to be that mu is equal to 60, and our alternative hypothesis H1 will be that mu is less than 60. If we let x equals the amount of juice in a carton, we assume H0, so x follows the normal distribution with a mean 60 and a standard deviation 3. This means that the sample mean, x bar, will be normally distributed with a mean of 60, but this time as a variance of 3 squared over 16, which was the sample size. Or, in other words, x bar follows the normal distribution with a mean 60, but a standard deviation of 3/4. We want to find the probability that x bar is less than 59.1, which gives us 0.1151 on your calculator. And as 0.1151 is greater than 0.05, our significance level, not less, there is insufficient evidence to reject H0, and so we cannot conclude that the mean amount of juice in the whole population will be less than 60 milliliters. If you need to find a critical value or region for a hypothesis test for the mean of a normal distribution, you can either use the inverse normal distribution function on your calculator to find the values or region for x bar directly, or you can standardize the test statistic. We have x bar follows a normal distribution with a mean mu and a variance sigma squared over n, then we code the data with z is equal to x minus the mean mu over the standard deviation, which in this case will be sigma over the square root of n, and this will be the standard normal distribution with z following the normal distribution with a mean 0 and a standard deviation 1. Coding in this way allows you to use the percentage points table for the critical values and regions in the formula booklet. Let's do one more example. A factory makes bolts with a diameter d, which is normally distributed with a mean of 0.580 centimeters and a standard deviation 0.015 centimeters. The machine is repaired, and afterwards a sample of 50 bolts is taken to see if the mean has changed. Part A. Find at the 1% level the critical region for this test, stating your hypothesis clearly. The mean diameter of the sample of 50 bolts is found to be 0.587 centimeters. Part B. Comment on this observation in light of the critical region. We're testing to see if the mean has changed, not if it's just greater or less than. So our null hypothesis will be mu is equal to 0.580, and our alternative hypothesis will be mu is not equal to 0.580. We're assuming H0, so we say that the diameters are normally distributed with a mean of 0.580 and a standard deviation of 0.015. This means that our sample mean, d bar, will be normally distributed with the same mean 0.580, this time a variance of 0.015 squared over 50, which was the sample size. We then need to code the data by letting z equal to d bar minus the mean, which is 0.580, and over the standard deviation, which will be the square root of all of this, or 0.015 over square root 50. We're testing at the 1% significance level, so that means in each tail, the upper tail and lower tail, we need to have half of that significance level, or 0.005. Let's find the lower tail first. We want the probability that z is less than z1 for the lower tail will be equal to 0.005. Using the inverse normal or the formula booklet, this will give you Z1 is equal to minus 2.5758. And so this is equal to D bar from the coding minus 0.580 over 0.015 over the square root of 50. And solving this gives D bar will be equal to 0.5745 and so on. For the upper tail, we want the probability that Z is greater than Z2 for the upper tail will be equal to 0.005, which solving in the same way will give us Z2 is equal to 2.5758, the positive version, as the normal distribution is symmetrical. And so this again is equal to D bar minus 0.580 over 0.015 over the square root of 50, which when solving gives us D bar will be equal to 0.5854 and so on. And so therefore the critical region will be D bar is less than or equal to 0.575 to 3SF, or D bar is greater than or equal to 0.585 to 3SF. Part B. The observed value of D bar, the mean, which we found as 0.587, does fall inside the critical region, as 0.587 is greater than 0.585. And so there is sufficient evidence at the 1% level that the mean diameter has changed from 0.580. And that's about it.